everyone. So what we're going to be talking about today is a little bit of radioactivity. We're going to talk about the different types of decay that can take place. So maybe you've heard of alpha and beta and gamma decay. So we're going to talk about the types of decay. And we're also going to talk about fission and fusion. So we started off the notes, and we were basically, I did a little bit of history with you, and there were three scientists, so a man by the name of Becquerel and his students, Marie and Pierre Curie, and there was some significance as to Marie Curie, and something with her and the Nobel Prize. Anybody remember what the significance is? She was the first what? First person to get 2 Nobel Prizes, and first woman to get a Nobel Prize. And do you remember what the Nobel Prize was? The first one that she shared with both Becquerel and Pierre, that was for finding what? Starts with an R. Finding what? Discovering radioactivity. Perfect. And her second one was actually for discovering 2 radioactive elements. Anybody remember what those 2 elements are? Radium and polonium. Awesome. For figuring out radium and polonium. And so that was there. There was an accident. And so I don't know if you remember what that accident was. They were trying to develop film, and what happened? Yeah, it was exposed. It appeared as if it were exposed. And so what did they figure out? What was stored in some drawer? Yeah, they had uranium salts. And these uranium salts are being stored in the drawers, and they found out that that's what was decaying and giving off this radiation. Let's talk a little bit about fission and fusion. So it says, while many elements undergo radioactive decay naturally, nuclear reactions can also be stimulated artificially. So although these occur naturally, we're most familiar with them as stimulated reactions. And there are 2 types of reactions that we're going to talk about. So the fission and the fusion. And we're going to start with the fission. So fission is reactions in which an atom's nucleus does what into smaller parts? Yeah, it basically just breaks up into smaller parts. And it releases a whole bunch of energy as this happens. Most commonly, what happens is you fire a neutron at the nucleus of an atom, and that neutron actually causes the atom to split up into parts. And when that atom splits, the nucleus splits into parts, it actually gives off other neutrons. And those neutrons will then hit into other nuclei, splitting those nuclei. And it's basically a whole chain reaction that takes place just from starting one. So as soon as one neutron is fired, then all of the rest of them start to split. So it says the energy of the neutron bullet causes the target element to split into 2 or more elements that are lighter than the parent atom. And so you get 2 lighter nuclei. And so this is a simulation that's basically going to show this. So you can see that there's a neutron that hits this nucleus, and that's your fission. It releases energy. And these are neutrons that are given off, and then 2 new nuclei. And those hit other nuclei, and then they split and break off into neutrons and other nuclei. And so you get this huge chain reaction. Okay? Now, this can either be done in a controlled setting, or it can be done in an uncontrolled setting. Okay? And so this is the difference between, you can have nuclear power that is controlled, and we can basically harvest all of that. And what is that? What is the plant called? It's called a nuclear power plant. Awesome. Okay. And there may be a group that's doing a presentation on nuclear power plants. So they'll be talking to you a little more about that. And then you can have an uncontrolled reaction. And that's what happens in what they call atomic what? Atomic bombs. Perfect. So let me just give you an idea of what that might look like. So we're going to see what in this case here, we've got a controlled reaction. So let's click on this. And what it says is, in a controlled fission chain reaction, such as that which occurs in a nuclear reactor, fissionable atoms make up a small portion of the fuel rods. And this allows the reaction to proceed spontaneously, but it's controlled. And so you get control rods and you have fuel rods. And basically, let's insert the control rods and see what happens. So you insert the control rods in here. And if we were to take a look at what was happening on the inside, if we could, you can see that you have a neutron that hits into other nuclei, but then it stops once it hits the control rods. So it says the reaction proceeds spontaneously with neutrons from nearby fission reactions stimulating other nuclei to split. And so when those split off, again, you get more neutrons that come off, and those hit into other nuclei. The reaction, however, proceeds in a controlled manner. The concentration of fissionable atoms is low. It makes up about 3 to 4% of the material in the fuel rods, and it allows it to be self-sustaining, but it prevents it from being an uncontrolled reaction where if the control rods are not able to keep this under control, that's where you can get a nuclear power plant to have a meltdown. And so when meltdowns happen, this is what happened at Nagasaki in Japan. And so we'll talk a little bit about that later. Maybe the group that's doing power plants may end up talking about that too. So additionally, control rods are used to temporarily quench the sustained reaction, and then heavy water is used. And so if there's a group that's doing power plants, they'll talk about how the heavy water is used in order to also assist in controlling the reactions. Okay, so let's take a look now at what an uncontrolled reaction would look like. So in an uncontrolled fission reaction, such as that in a nuclear bomb, each nuclei undergoing fission releases 2 to 3 neutrons, which then stimulate additional fission reactions. And that makes up 80% or more of the fuel in this scenario. So let's take a look at what happens here. So if we were to look at this, we don't have control rods anymore. And so what happens is you see that very, very quickly, they all end up reacting, and eventually you get that mushroom cloud. Okay? Again, if there's a group that's going to be doing atomic bombs, then you'll hear more about that, and different types of bombs. So they'll talk about, there are different names for the different bombs, so I'll let them talk about that. Each nuclei undergoing fission in an uncontrolled reaction stimulates 2 to 3 additional reactions. And so if you don't have the control rods, then you get an increased concentration of the atoms, and so it multiplies exponentially. So one atom stimulates 3, and then those stimulate 9, and then that stimulates 27, and then you can see that really quickly it happens where it increases so quickly. So since each step takes fractions of a second, within milliseconds, billions of nuclei fission simultaneously. So right at the same time, you get billions of these fission reactions happening. And it releases a huge amount of energy and heat. And so that's how you get this rapid expansion, and you get that huge mushroom cloud. It says it causes rapid expansion of the surrounding materials, and then a nuclear explosion results. Okay, so let's come back to the notes. And that's basically it. So let's just write down here. We can either have a controlled fission reaction, and like where? Where is a controlled one? Where would that take place? Yep, in nuclear power plants. Nuclear power plants, where they have control rods. Or it can be an uncontrolled, and I'm just going to write the first word and then I'll do quotes. Uncontrolled fission reaction, like what? Yep, nuclear bombs. Okay, so these are both fission reactions in both scenarios. All right, so let's flip. And on the right side, now we've got nuclear fusion. So these are reactions in which 2 or more elements do what? What does fuse sound like? They're coming back together. So fusing is coming back together, whereas fission is breaking apart. So it says they fuse together to form one larger element, and this also releases energy in the process. So both processes will release energy. The thing with fusion, though, is we can't get fusion to happen on Earth. Where does fusion happen then? Yes, where? On the sun. Perfect, that's where fusion happens. Nice, on the sun. Okay, so let's take a look at what happens there. It says a good example is the fusion of 2 heavy isotopes of hydrogen, deuterium and tritium, into the element helium. So let's take a look at this one. So this is deuterium. So when we look at deuterium, we can see that it's got a mass of 2, which means we know that hydrogen has a 1 proton. So what's the other thing that's there? 1 neutron. Perfect. And then up here we have something called, anybody want to guess what this is called? Tritium. Nice. This is tritium. So there's just regular hydrogen, and then they'll call it deuterium or tritium. Why tritium? Well, the mass is 3, so hydrogen always has how many protons? 1. But then what else does that have? 2 neutrons. Awesome. And so what we're going to see here, if we play this, is these 2 are going to come together, and that's the fusion reaction that ends up releasing a whole bunch of energy. So let's replay this one more time. So we can see we've got tritium, we've got deuterium. They're going to come together and fuse together. That's fusion. And then they break off, and what happens? So what we have in the end here is we've got 2 protons, which means it's what element? What element has 2 protons? Helium. And then we also have 2 neutrons. So what would the total mass of this be? 4. Awesome. Okay. Now, it's a helium nucleus. Even though helium would normally have 2 electrons, right? Because what do you know about the noble gases? They're stable and they don't want to bond. So we know that the diatomics are stable and they absolutely don't want to lose or gain any electrons. So helium would normally have 2 electrons on it. So they just say it's a helium nucleus. And where does this take place? This takes place, this is fusion. Where does fusion take place? On the sun. Okay, awesome. We have not been able to replicate it here. There is something, anybody know what it's called? It's a really easy word. So fusion is really, really, really hot. And so they actually they try to get this to happen on Earth, and guess what they call it? Not hot fusion, but cold fusion. How many of you have heard cold fusion before? So they're trying to get cold fusion to take place on Earth where you're fusing nuclei together, but in an environment that is sustainable here on Earth, where we can't get those temperatures. So there's something called a tokamak, I think it's called, and that's where they're trying to do that. Okay, so let's come back to the notes here. All right, and down here, so we can see that we've got this. What's this called then? It's the 3 one. So that's called what? Tritium. Good. And this one up here is called deuterium. Very good, deuterium. And over here, then what is this? This is coming together to form what in one nucleus? Helium. And so just write the sun on here. Okay, so that's the process that would be taking place on the sun. All right. So next what we're going to be talking about is nuclear chem and the belt of stability. So it says most elements have different isotopes, and we talked about isotopes at the beginning of the year. An isotope has the same number of something, but a different number of something else. Do you remember what is always the same about an isotope? It's number of? Protons. Awesome. We said isotope, isoprot. So the protons are the same, but it's got a different number of what? Neutrons. Awesome. And so if the neutrons are different, for example, you could have carbon 11, you could have carbon 12, you could have carbon 13, you could have carbon 14. What number goes on the bottom of each one of these? The atomic number, which is what for carbon? 6. So that's a 6, 6, 6, and 6. So you can see that the protons are always the same. But if the neutrons are different, then you add your protons to your neutrons. What do we call that top number? The overall what? The mass. Very nice. That's the mass. So it says, therefore, they're the same element, but it's just a different mass or a different mass number. Okay. For stable isotopes, an interesting plot arises when the number of neutrons, so this here is going to be our number of neutrons, is plotted versus our number of protons. Okay? It's not mass to protons, it's neutrons versus protons. So be careful with this, because when you look at the periodic table, keep in mind that if you were to look, for example, at nitrogen, that 7 we know represents our atomic number, so that's our number of protons. This 14 is not your number of neutrons. What would that 14 be? Mass number, which is protons plus neutrons. Now, really it's not the mass number. If we took an average of it, we would call it the mass number, but this is called the atomic weight, and keep in mind that that's an average of all the isotopes as they exist in nature. And we had done that calculation at the beginning of the year when we did shift your decimal, 2 loops back, multiply by the mass, add the numbers, shiggity shag. That's how they got that number. So remember, that's called the atomic weight or the atomic mass. If you want just the mass number, it's just for one isotope. It's the protons and the neutrons. Okay, so what we're looking at on this graph is not the mass. We're looking at the neutrons. How do you get the neutrons? If you know the mass and you know the protons, then how do you get just the neutrons? For example, here on carbon 14, you subtract. So it'd be 14 minus 6, which would be 8. Okay, so couple of things on this. The first thing is this line that's going here, right here, this is actually just a reference. And what this reference is showing, anybody read what it says on there? Yep, it's a 1-to-1 neutron to proton ratio. That's just showing your 1-to-1 ratio. So that's just used as a reference, okay? This here, this whole thing right here, this is actually representing what we call the belt of stability. Now, just based on the name, what do you think that this is indicating? What do you think this is depicting, this belt of stability? What do you think?
Stable atoms.
Stable atoms, stable isotopes. Perfect. What this is showing is, this is showing the atoms that would be stable, or the nuclei when they're stable. And so what we do is we check to see how many protons does it have and how many neutrons does it have. If you can match it up and it falls right on the belt, that's a stable nucleus. If you match it up and it doesn't fall on the belt, what's going to happen to it is it is going to decay, radioactively decay, until it reaches a more stable place. Now, this mode of decay, a lot of times it takes like 12 steps. It doesn't just happen in one step where it starts here and it ends up at the belt just in one step. A lot of times there's a whole series, and they'll call it a radioactive decay series, and at the end of the notes we'll actually do one together and see if we all come up with the same answer. So it says, for stable isotopes, an interesting plot arises. So it says, because the plot shows only the stable isotopes, this graph is called, what did we call this? The belt of stability. Perfect. The plot indicates that lighter isotopes are most stable when the neutron to proton ratio is 1-to-1. Just circle neutron to proton and 1-to-1. So let's come down here. And we can see that if we could draw a line from 20 and then meet where 20 meets, so just draw two lines from 20 to 20, what do you notice about our reference 1-to-1 line and our belt of stability? What do you notice about it? They're pretty much the same, okay? And so what they say is, for elements 1 to 20, we don't have an element 0, right? So for elements 1 to 20, they basically are very stable when their number of neutrons are also equal to 20. Well, that makes sense, because when we go back to a periodic table and we look at these elements, if you look at something like calcium, for example, calcium's got 20 protons. If the mass is 40, that's the one that's closest to the average that has the greatest abundance, percent abundance, then how many neutrons is 40 minus 20 is 20. So if you have 20 protons, you have 20 neutrons. But if we were to look at something like, I don't know, let's look at palladium, number 46. The mass is 106. What's 106 minus 46? 60, right? So now you're not at a 1-to-1 ratio anymore. Now you're looking at something more like 1 to 1.5 is basically what you're looking at. So number of, what we're looking at is our proton to neutron, or 1.5 to 1 if we're talking about neutron to proton ratio. It says, this is the case with any nucleus that has up to 20 protons. As the atomic number increases beyond 20, once we pass 20, it appears that a stable nucleus is actually able to accommodate more neutrons. So once you pass 20 neutrons, your nucleus can actually have more neutrons, and that keeps it stable. And it says the neutron to proton ratio basically goes 1.5 to 1 for the stable isotopes between 20 and 83. So if we look on this graph, we can see that once we hit this point up here, our belt kind of ends. And if we draw a line coming straight down, that's basically 83. So the question is, what happens after 83? Well, after 83, we say that they actually are all what?
Radioactive.
Radioactive. Awesome. Once you pass number 83, elements past number 83 are all called radioactive, okay? And all of those are going to try to decay until they come down the belt. So where is number 83, just for those of you looking for it on here too? So we're looking over here at bismuth. So anything that basically is coming after bismuth, we're going to say is going to radioactively decay. All right, we're going to come back to the periodic table in just a second here. What is this called again? The what? Belt of stability. The belt of stability. It helps to predict how radioactive isotopes will decay. The typical modes of decay, we're going to talk about these right now, are alpha, beta, gamma. There's something called positron emission. There's something called electron capture. We're not going to talk too much about electron capture, but we will talk about the other four. The atoms will decay until they reach a more stable isotope, one that falls on the belt of stability. Okay, before we talk about the different types of decay, please take a look at your periodic table again. And I'm just going to read this with you. So it says selected radioactive isotopes, and that's what's showing right here. And a lot of you probably have never really noticed that this was there. So let's read through this together to see what this is, what this table in the middle of your periodic table, what this is. It says naturally occurring radioactive isotopes are designated by a mass number in blue, although some are also manufactured. So you can see that some of these are in blue, and then it says some of them are manufactured. Letter M indicates an isomer of another isotope of the same mass number. Half-lives follow in parentheses. So after, you can see that there are parentheses, and so this is representing what is called a half-life. We haven't spoken about that, so I'm going to see if maybe you can tell me what you've heard what a half-life is. It says, where S, min, H, D, and Y, what do those stand for? Time. Like, what do you think S is?
Second.
Min, H, D, and Y, years. Perfect. Respectively for those different, whatever their abbreviations are. The table includes mainly the longer-lived radioactive isotopes. Many others have been prepared. Isotopes known to be radioactive with half-lives exceeding 10 to the 12th years are not included. So if they have a really, really long half-life, those are not being shown in this table. Symbols describing the principal mode or modes of decay are as follows. This little, it looks kind of like a fish, that's called alpha, so that's alpha particle emission. This B is called beta, and so there's beta minus, and then there's beta plus. Beta plus is called positron emission. We're going to go through these. EC we're not going to talk about. It's called electron capture, orbital electron capture. IT is called isomeric transition. We're not going to really talk about that. And SF is called spontaneous fission. So let's look at some of these. Let's take a look maybe at the carbon one. So we've got carbon 11 and carbon 14. Are there other isotopes of carbon that exist? Yes. But what they said was they selected certain ones on this table, so they're not showing us all of them. Okay? And the other thing that I wanted to make sure that you got to that I skipped over on here is it says these processes are generally accompanied by gamma. So they actually don't tell you, but gamma is another form of radiation, of emission, and they're saying that most of these that they're showing you here actually have gamma radiation as well. Okay, so let's take a look at carbon. So carbon 11, and you know this, it always has 6 protons, okay? So carbon 11, it says 20.40 min, beta plus, and carbon 14 says 5730Y and beta minus. Okay, so let's talk about what this 20.40 minutes and this 5,730 years, what do we think that means? So they told us that's the half-life. Anybody, maybe in your math class, you started talking about it, or maybe in your science classes before, you've talked about what this half-life is? Anybody want to take a guess at what this half-life, what is this half-life? Yep, go for it.
Time it takes for half of the element to decay.
Perfect, that's exactly it. It is the time it takes for half of some substance to decay. To decay by how much? By 1/2. For example, I want to make sure that you don't get any misconceptions because it's very common to get misconceptions with this. Let's say you start with 200 grams of something, okay? So after one half-life, let's say a half-life is 10 days, okay? After 10 days, if you started with 200 grams, how much do you have now? 100 grams. Okay, so another 10 days go by. And after another 10 days, you don't have 0. It's not you're going to decrease by 100 every time. Now you have 100. Now what's half of 100? 50. Now you're at 50. After another 10 days, how much do you have? 25. After another 10 days, how much do you have? 12.5. And then you're going to get 6.75. You're going to keep on decreasing. And they say that in theory, you would never basically come to what? 0. In theory, you would never get to 0. You would keep on splitting in half, in half, in half, in half every half-life. So let's come back to this here. That means that carbon-11, in 20 minutes, half of it is gone. So if you started with 100 grams of it, in 20 minutes, how much do you have? 50. Okay. In a couple days, what would you expect? You wouldn't be able to see it. Okay? You wouldn't be able to see any of it. Whereas carbon-14, how long does it take that to decay in half? 5,730 years. Carbon-14, anybody know what that's used for? It's actually used for, take a guess. For dating. It is used for radioactive dating. That's what it's called. And so we'll talk more about that too later in the unit as well when we start doing our half-life calculations. But carbon-14, like when they tried to date the sea scrolls, for example, that's what they used was carbon-14 dating. So we'll talk more about that later on too. So you can see that these all have different modes of decay. What you'll probably notice is you don't see any alpha for the most part, in any of these. Where do you start seeing alpha? Anybody see alpha somewhere on here? Once you get to basically what number? Yeah, so once we start getting over into, I'm seeing it maybe here in this area, I'm seeing alpha right here at 146. I see a whole bunch of alphas over here and over here, okay, where we start seeing some alpha decay. So, yeah, right around like bismuth and down here, we can start seeing there's alpha decay at number 64. That's got some alpha decay. All right, so let's come back to the notes, and we'll come back to the periodic table after too. So let's talk about this alpha decay. So the alpha symbol right here, I want you to redraw it. So we're going to make an alpha symbol. Kind of looks like a fish, a little bit like a fish. And the alpha particle is actually a helium nucleus. Well, we just talked about helium. How many protons does helium have? 2. And so down on the bottom here, we're going to put a number 2 to the left on the bottom. And the top number, helium has 2 protons and 2 neutrons. So what's the total mass? 4. So helium's a 4 too. So you can either call this alpha or you can write He for helium. It's the same thing. So during alpha decay, a helium nucleus is released. And so what we see here is uranium-238 does this. And so what we have is uranium-238, we know that it's got 92 protons, it always has 92 protons. It's going to give off what is called an alpha particle. That's our alpha particle right there. And by the law of conservation of matter, you're going to be able to tell what the particle is that it decays into, simply by saying, well, if I know that my mass needs to equal 238, then on this side, if that's 4, what must this number be? What does it say? 234. And if this is a 92, then on this side, these have to add up to equal 92. And if that's a 2, then this must be a 90. So let's try another one, okay? So let's pick, on the periodic table, let's pick any one of these that goes through alpha decay. Maybe let's do, I don't know, lead-210, okay? Lead-210 goes through, actually that goes through alpha and beta too. Let's pick one that just does alpha. Bismuth-210, okay. So let's come back here and let's write bismuth-210. So Bi, and if it's dash 210, then that's the number that goes on top. We can always figure out what bismuth's atomic number is from looking at the periodic table, and bismuth is number what? 83. Perfect. You're going to draw an arrow, and then a lot of times they'll put the type of decay above the arrow, okay? So that would be saying that it's going to go through alpha decay. All right, and then let's write an alpha particle. So the alpha particle is, you can either write helium, or you can do that fish symbol, and what number goes on top? 4, and what number goes on the bottom? 2. Plus something. Now, what's going to happen is you need to figure out what this something is, okay? Either they'll give you what you're starting with and what it decays into, and you have to figure out the particle, or they give you the particle and you have to figure out what it decays into. So, if this is 210, and by the law of conservation of matter, this side has to equal 210. 4 plus what is 210? 206. Awesome. Bottom number. This side's at 83, so what must this side be? 81, because 81 plus 2 equals 83, so they have to be equal. Now, how am I supposed to figure out what this element is? So let's take a look back at the periodic table, and element number 81, if you look at the periodic table, is what? Thallium, Tl. And so that's how you get the symbol for it. Then you write Tl. Okay, be careful, it's not an I. That would be titanium, so it's Tl. these alpha particles, if you simply had a piece of paper, you can stop an alpha particle, okay? So all you need is a piece of paper or anything that's more dense than paper. So paper or anything more dense, that will stop an alpha particle. So what happened to it? The mass number, or the top number, it ended up decreasing by how many? How many did the top number decrease by? By 4, perfect. And the number of protons at the bottom, did that decrease or increase? That also what? Decreases by 2. Okay, so in alpha decay, that's what happens. As an alpha particle is emitted, the number of neutrons and protons both decrease, and it creates a more stable atom. And so depending on where you are in the belt, it may go through alpha decay to try to decrease to come to the belt. All right, let's talk about the next one. The next one's called beta. And you can either write it as beta minus or just beta. So you're going to draw this B, but it kind of has this like little attachment at the end of the B. Okay, so what happens in beta decay, I'm going to explain it first, then I'm going to give you the shortcut. Okay, the scientists came up with a shortcut for this. What happens is, inside of your nucleus, one of the neutrons in your nucleus turns into a proton. What do you know about the mass of a neutron and a proton? They're about the same. So, does your mass change? No. But what do you know about what's different that you know of a neutron versus a proton? The charge. Awesome. The neutron doesn't have a charge, but the proton's charged +1. So what they basically end up saying is, they say that a neutron turns into a proton, and they say that an electron, or a high-speed particle, they call it a beta particle, they say that an electron is ejected from a nucleus. What? Are there electrons inside of the nucleus? No, we know that electrons spin around the nucleus, so it doesn't really make sense, but the particle that's emitted, it looks like an electron. Meaning, does it have mass? No, it does not have any mass. And what's the charge of it? -1. So what this beta particle looks like is it basically looks like an electron. The mass goes on top, so that's a 0. And what about the number of protons? Well, it doesn't have protons, so it's actually -1. And this can also be written as an electron with 0, -1. So you can write it either way, and that would be called the beta particle. So it says there's the disintegration of a neutron into a proton, and a beta particle, or a high-speed electron, increases the atomic number by 1. So let's see how this happens. Carbon-14, we were talking about carbon-14 dating, and that's where this goes through beta decay. So you can see that carbon-14, what happens to the mass number when it gives off an electron? Stays the same. So our mass is still 14. Now the number of protons, it was 6, but if the electron is a -1 and these two have to equal this side, then this number is actually a 7. And so then you look on the periodic table and you figure out, well, what's atomic number 7? That means that carbon is actually turning into nitrogen when it decays. And so we'll talk about that later and how that, what the significance is of that with carbon dating. Let's try another one of the beta particles. So let's take a look on the periodic table, and maybe let's do something like, we could do any one of these. We've got chlorine 38. Cl38 is going to go through beta decay. Okay, so let's try one. We've got Cl38, and the number of protons in chlorine is always what? 17. So we're going to do an arrow, and we're going to do our beta particle right there. So let's draw a beta particle first. So it's going to be a B, or an electron. The top number again is a 0, and the bottom is a -1. Plus something. So now we have to figure out what this something is. So what about our top number? Still 38, because 38, and this is 0 plus 38. And now the bottom number, if that's 17, -1 plus what is 17? 18. Awesome. So it actually increases by 1. So then you're going to look at your periodic table, and what has atomic number 18? Argon. Argon. Perfect. And that's what it's decaying into. Okay. Beta particles can be stopped. It has to be something, it'll go through paper. Okay. They're smaller than alpha particles, so they're actually small enough to pass through paper. You can stop them either by a piece of wood, or you can get a piece of metal, like aluminum foil works. Aluminum foil is something that they'll use to stop beta particles. All right. It says the net effect is that a neutron becomes a proton. We already talked about that, so just underline that or squiggly line it. By ejecting an electron. The result of beta decay is that the mass stays the same, but what happened to our neutrons? So if a neutron turned into a proton, then our neutrons did what? Decrease by how many?
1.
Yep, number of neutrons decreases by 1, while the number of protons does what? Increases by 1. Perfect. And your neutron to proton ratio decreases, and so you end up getting closer to the belt. So for example, if you have something like chlorine 38, then how many neutrons do you have? If you subtract this, what do you get? 17 plus what is 38? Yeah, what did you say? 21. Perfect. So that's 21. So we would basically say we've got 17 protons, which would be somewhere along here. Okay, so about 17 protons. And then we're going to come up to 21, which means that we're basically coming about to this point. And what's going to happen is it's going to decay so that it can come closer to the belt. So one of the neutrons will turn into a proton. And if one of the neutrons turns into a proton, then how many will you have? How many protons will you have then? Instead of having 17, you'll have 18. So this bumps up by 1, and this comes down by 1, and so now you're closer to the belt to make it more stable. And it'll keep going through decay until it gets closer and closer to the belt. Positron emission is really easy because it's exactly the opposite of this, but it's the same type of particle. So instead of being a negative electron, it's a positive electron. Okay? So what's the mass of it? It's still what? 0. And you have to have a plus sign on this one. So this one you don't have to have a negative, but this one you have to have a plus. Okay? And instead of being a negative one, it's a plus 1 down on the bottom. So that's your beta particle. Again, you could write it as a positive electron as well. So positron particles have the same mass of an electron, so barely any mass, but they have a plus 1 charge. When a positron is ejected from the nucleus, what happens instead of a neutron turning into a proton is a proton turns into a neutron. So again, what happens to the mass? Still the same, perfect. But if a proton turns into a neutron, it actually, one of the positive charges is gone, and so you're getting a neutron instead. So look what happens here. This is like carbon 11 will do this. So you can see, start with carbon 11, the mass stayed the same, it's still 11, but what happens here? 5 plus 1 equals 6, and so now your number of protons actually decrease by 1. So that's what positron emission would be. Now let's take a look at gamma. So gamma emission usually accompanies all of the above decay processes. So they said that on the periodic table too. They said that almost all of those would be experienced in gamma. You've heard gamma before. Remember, run, Mark, what? It's Vicky, your ex-girlfriend. And gamma was at that far end where X-rays are. It's even further out. Those are very high energy particles, okay? So really high energy, and the thing with gamma is gamma has no mass and no charge. So when you draw a gamma symbol, it kind of looks like a Y a little bit, the letter Y. It has 0 mass and 0 charge. So you're probably looking at that and thinking, then why even care about it? Who cares about gamma? Why would we even include it? The reason why you would include it is gamma is actually the most what of all types of particles?
Radioactive.
It's the most damaging and the most penetrating of all of them. These are very penetrating, and they're so small and they're so light that they will actually come right through you. And when they pass through you, guess what they do to your cells?
Mutate them.
They mutate them. And what do we know? What happens when you have a whole plethora of mutated cells that are uncontrolled? That's cancer, okay? And so that's the danger of gamma. So what can we use to stop gamma? Similar to X-rays, what can we use to stop X-rays? You can wear what kind of jacket when you go to the dentist's office? Lead, perfect. It's stopped by lead. Or back in the 80s, there was this whole scare of atomic bombs. And so they had what were called bomb shelters. And they were basically underground, and it was like being in a basement with layers of concrete. So you can either use layers of concrete that would provide protection, or lead, like a lead jacket would provide protection. So when you have gamma radiation, it's actually all of them together. So you could have any of the processes take place, and basically you would just say, after your arrow, you would just say plus gamma. So it'd be gamma plus, let's say alpha, where it's a 4-2, plus something else, okay? So you would just show it that way. You can write the 0, 0 in, doesn't matter. All right, so let's just summarize these types of radiation that we just talked about. So alpha. The symbol for alpha is simply just that like fish symbol. And what's the top number? You need to memorize this. It's a 4, and the bottom number is a 2. Awesome. And so we can also call this helium. It's just a helium nucleus. The speed of it. They say that this is about a 10th the speed of light. It's about the 10th the speed of light. It can be stopped by what type of matter? What do we say you can stop alpha particles with? Paper. Piece of paper, or anything more dense than paper. And the last thing is the charge of it. Well, it doesn't have any electrons, and neutrons don't have a charge. So what is the charge of it? Positive what? 2. Why positive 2? 2 protons. Awesome. 2 protons in the nucleus. So that's a +2 charge. Beta. Let's do beta on this side, and let's do positron on this side. Okay. So beta is just that B, and then what's the top number? 0, and the bottom number? -1. What about a positron? Beta plus, so what's the top number? 0, and the bottom number? +1. Awesome. The speed, they say that it's approaching the speed of light. Approaching speed of light. Do you remember what the speed of light is? 3.00. Do you remember? Times 10 to the what? 10 to the 8th. Good. And what are the units of it? Meters per second. Meters per second. Awesome. Or you could do centimeters per second times 10 to the 10th. What can you stop beta and positron by? A piece of wood or aluminum foil. Good. Aluminum foil works. And the charge of it, it's like an electron. So what's the charge of it? Negative. So it's like, this can also be called an electron, an E-. And the last one is gamma. And so the symbol for gamma is just 0, 0. And this is at the speed of light. Because remember when we did the electromagnetic spectrum, we said that those were all traveling at the speed of light. And these can be stopped by what? Lead or concrete. Good, layers of concrete. Okay, and the charge of gamma, is there any charge? No. Nope, no charge. All right, so we're going to try these together. Let's first start with this one. We're going to do this one together, and I'm going to have you do these 3 alone, and we'll see if you can get these right. So if it says neon -24, remember what the dash is? That's giving you your mass, so that's the top number. That's the 24. How am I supposed to figure out the bottom number? Periodic table. So let's take a look at neon, and what's neon's atomic number? 10. So we've got a 10 down in the bottom. Arrow. It goes through alpha and gamma. So right on top of my arrow, I'm just going to put an alpha symbol, comma, I'm going to put a gamma symbol. So I'm going to put the alpha and the gamma on there. Let's do the alpha first. So the alpha has what numbers? What's the top and bottom? 4 and 2. Awesome. Memorize it. Okay, 4 and 2. Plus, gamma is what? 0, 0. Plus, now we have to figure out what it's decaying into. So we know that neon is going to decay. It's going to go through alpha and gamma. And the question is, what does it decay into? So by the law of conservation of matter, the number here to the left of the arrow has to be equal to the total on the right. So if this is 24 and that's a 4 and a 0, what must this be? 20. Awesome. Bottom number. If that's a 10, 2 plus 0 plus what equals 10? 8. So now let's take a look at the periodic table. And what has atomic number 8, everybody? Oxygen. Awesome. Okay, so let's take a quick little break here so that you can try these 3 out, and then we'll come back and check our answers. Okay, so we have people come up and do these, and these are all done correctly. For B, we got silicon, so simply because the beta is a -1, so -1 plus 14 equals the 13. Here we got the platinum, because we want 78 plus 1, 79 to equal the 79 on the gold. And down here we got uranium 240, because in this case we want the 90-40 equal the 2 plus the 92. Okay, what I want you all to do is, if you can please pull out your Intro to Nuclear worksheet, and if you flip it to the back on here, there is a radioactive decay series, and I want you to try this out. So what you're going to do is you're going to start this off, and you're going to figure out what A is. And once you figure out A, I want you to plug A into here, and you're going to do this chain reaction until you come to a stable isotope. You can see that it's taking a whole bunch of steps to come down to this stable isotope. And so go ahead and try this out, and then we'll end up figuring out if you guys all got the answer right. Okay. Okay, and the answer that you should have gotten, everybody, was what? HG. Awesome. So if you got that, great job. That you did incorrectly. So maybe it was just like this one up here. Maybe it was the very first step that you may have made a mistake on. So if you need to pause it, you can do that in the video. And that's basically it for the different modes of decay.